Hello everyone, we are Soyeon and Yin. Today we are going to present our research on building a bloodstain pattern analysis and blood droplet behavior prediction model based on a hypothetical crime scenario. This study assumes a case where the victim B was found dead after allegedly sleeping on the stairs. The suspect A claims that B was carrying a laundry basket when he slept on the wet stairs and hit his head on a wall-mounted shelf. However, the distribution and pattern of the bloodstains at the scene suggested that it was not a simple accident fault. Investigators identified several inconsistencies in A's statement and raised the possibility of external force being involved. The severity of the bloodstain was inconsistent with a mere head injury from hitting the shelf. The bloodstain distribution suggested the presence of a strong external force. A remained calm when calling emergency service, but did not check B's condition. Additionally, the stairs showed minimal traces of moisture, contradicting A's claim of recent cleaning. Given these circumstances, it was suspected that B did not simply fall, but was pushed, leading to fatal trauma. To verify this hypothesis, we conducted a scientific analysis of bloodstain patterns and droplet behavior.
Crime scene investigations are often complex, and conventional forensic techniques have limitations. If you think about DNA analysis, for instance, it can determine who was present, but not what they did. Additionally, it does not provide time-related information about bloodstains, making evidence tampering difficult to rule out. So here, bloodstain pattern analysis, also known as BPA, allows for a more precise reconstruction of the crime scene's physical events. This study focuses on critical aspects of a crime that cannot be fully explained by other forensic methods. However, BPA often relies on empirical analysis, lacking a quantitative and objective approach. Therefore, this study sets up fluid dynamics and physics-based principle to analyze the velocity and direction of blood spatter more precisely, aiming to reconstruct the physical characteristics of the crime scene more accurately. By establishing a stimulated crime scenario and analyzing bloodstain formation through mathematical modeling, our goal seeks to enhance the reliability of BPA and demonstrate how quantitative approaches can contribute to forensic investigations. The contact angle characteristics of a droplet on a solid surface are determined by the relationship between the surface energies and the interfaces of the solid, liquid, and gas phases. Unlike a stationary droplet which maintains a uniform contact angle across the entire contact surface, a moving droplet exhibits different contact angles at the advancing front and the receding rear. To analyze the behavior of blood droplets on a surface, the capillary number can be used to distinguish between advancing and receding motion, allowing for the formulation of appropriate equations. Here, UCL represents the velocity of the contact line of the droplet on the solid surface. When the capillary number is positive, it indicates that the contact line is undergoing advancing motion, whereas the negative value signifies receding motion. This equation provides a model for calculating the dynamic contact angle based on the determined capillary number we interpreted beforehand. It describes how the contact angle changes as the fluid moves, allowing for the prediction of dynamic contact angle variations. When the contact line moves, the dynamic contact angle at the interface between the fluid and the solid surface starts from the static contact angle, which represents the contact angle when the fluid is at rest. To account for the movement of the contact line and the interactions between viscous forces and surface tension, the capillary number is divided by the dynamic contact angle, viscous forces, and surface tension. The capillary number is divided coefficient k and then raised to the power of 1/3 as an approximation. Typically, the value of k equals to 9 times 10 to the power of minus 9 for advancing behavior and 9 times 10 to the power of minus 8 for receding behavior. Based on these conditions, the droplet ultimately exhibits the following contact angle characteristics. When the capillary number is positive, it indicates that the contact line is undergoing advancing motion, whereas the negative capillary number signifies receding motion. The advancing contact angle represents the upper limit of the advancing contact angle, which is the maximum angle beyond which the fluid can no longer spread on the surface. When the capillary number is positive, meaning that the contact line is advancing, then the dynamic contact angle is determined by selecting the smaller value from the minimum function. As a result, if the selected value is equal, it indicates that the contact angle has reached its upper limit, preventing further spreading of the fluid on the surface. On the other hand, if the selected value is dynamic contact angle equals to dynamic static angle plus capillary number divided by k advancing angle, the contact angle increases proportionally to the capillary number reflecting the advancing motion. This idea applies to receding contact angle as well, which represents the lower limit at which the fluid can no longer detach from the surface, indicating the minimum angle. But in this case, you need to select a larger value from the two options in the maximum function. In their interpretation of the behavior characteristics of blood droplets shown in the following figure, the advancing angle is 120 degrees, the receding angle is 30 degrees, and the static angle is 90 degrees. The contact angle is applied to the blood droplet moving along the inclined plane, and the variation in behavior based on the contact angle can be observed in panels B and C. To predict the formation of bloodstains on a surface, it is crucial to consider the wetting characteristics of that surface. In this study, a scalar source term was applied to the prism mesh layer, representing the floor surface to incorporate the wetting characteristics resulting from the absorption of blood into the wall surface. We analyzed two contrasting types of surfaces, absorbent and non-absorbent surfaces, based on the behavior of the fluid. Here, AN and AN-1 represents the sizes of the space occupied by the blood droplet at the current and previous time steps, respectively, in the calculations of transit phenomena. In other words, S scalar is the value that represents the rate change of A over the time interval delta t, expressed in a differentiated form using an approximation. In the case where the blood droplet falls on paper, as shown in the following picture, the absorbent nature of the paper causes the droplet to be quickly absorbed, resulting in a decrease in the size and a rapid reduction in the area or volume of the blood droplet. Here, AN-1 is smaller than AN, indicating that the size of the blood droplet decreases sharply over time, leading to an increase in AN-1 minus AN. Consequently, the rate of change S scalar exhibits a large value. The glass surface is non-absorbent, allowing the blood droplet to remain on the surface without being absorbed. In the initial stage, the blood droplet spreads, causing a slight increase in the size of the droplet. Once it reaches a stable state, the size changes halts. During the initial spreading phase, AN-1 minus AN can be negative, and the scalar S scalar may be small or negative. In the stable phase, AN-1 is similar to AN, and the rate of change S scalar approaches 0.
The impact angle is a key factor in determining the pattern of blood droplets striking a surface. To analyze this, we examine blood stain patterns at 5 different angles: 90 degrees, 75, 60, 45, and 30 degrees. The predicted behavior of blood droplets under these conditions is shown in Figure 1, while Figure 2 illustrates the resulting impact patterns. The analysis revealed that as the impact angle decreases, blood stain pattern transition from circular to elliptical with an increasing difference between the major and minor axes. Additionally, fingering effects become more pronounced in the direction of impact, though the overall number of these patterns decreases. When a droplet strikes a surface perpendicularly 90 degrees, the resulting blood stain is circular. At oblique angles, the stain becomes elliptical due to the decomposition of the droplet's motion into vertical and horizontal components. The ratio between the minor axis D minor and major axis D major of an elliptical blood stain corresponds to the sign of the impact angle. Sin alpha equals to D minor divided by D major. By measuring this ratio, the original impact angle can be estimated, providing valuable insights into droplet's trajectory. At alpha equals to 90 degrees, the droplets fall vertically, producing a circular stain D minor equals to D major. At alpha is smaller than 90 degrees, the droplets impact at an angle, forming an elongated stain. The smaller the angle, the more stretched the pattern. By analyzing the major and minor axes of blood stains, this study presents a quantitative method for determining impact angles, enhancing the accuracy of forensic blood stain analysis. The diameter of a blood droplet affects its momentum upon impact, which in turn influences the size and distribution of the resulting blood stain. To analyze this effect, droplets ranging from 1 mm to 10 mm in diameter were tested under a constant impact velocity of 3 m per sec at four different impact angles: 45, 60, 75, and 90 degrees. The resulting showed that as the droplet diameter increased, the size of the bloodstain and the prominence of finger effect become more noticeable. Interestingly, the relationship between the initial droplet diameter and the resulting stain size was not strictly proportional. Instead, the ratio of the bloodstain diameter to the initial droplet diameter increased with larger droplets, indicating that greater momentum led to more extensive spreading upon impact. Apart from diameter, impact velocity also plays a crucial role in determining the droplet's momentum. To study this, we varied the velocity from 2 m per sec to 7 m per sec, while keeping the droplet diameter fixed at 2.5 mm, again testing at impact angles of 45, 60, 75, and 90 degrees. Similar to the diameter results, increasing velocity led to larger bloodstains and a higher ratio of stain diameter to droplet diameter. However, this increase plateaued at higher velocities, suggesting a limit to spreading effect caused by impact force. Bloodstain patterns are influenced by multiple factors, including both droplet size and impact velocity. To quantify their combined effects, we analyzed bloodstain patterns in relation to the dimensionless Rayleigh numbers, which describes the balance between inertial and viscous forces in fluid dynamics. Rayleigh number is defined as the product of blood density, impact velocity, and droplet diameter. A higher Rayleigh numbers indicates a dominance of inertial forces over viscous forces, leading to greater splattering and more irregular stain shapes. In this study, we adjusted blood viscosity to generate 7 test cases while maintaining a droplet diameter of 2.5 mm and impact velocity of 3 m per sec across 4 impact angles. Results indicated that lower viscosity led to greater spreading of bloodstains, showing a direction correlation between Rayleigh numbers and stain size. However, the occurrence of finger effects remained relatively constant across different Rayleigh numbers values. Notably, at an impact angle of 45 degrees, splashing did not occur at lower Rayleigh numbers values, meaning no finger effects were observed. The Weber number represents the ratio of inertial forces to surface tension and is another crucial factor in bloodstain formation. When Weber number is bigger than 1, droplets spread extensively and create complex stain patterns, whereas when the Weber number is smaller than 1, results in more uniform bloodstains due to the dominance of surface tension. In this study, we were controlled by adjusting the surface tension coefficient while keeping the droplet diameter and velocity constant. The analysis of 4 impact angles revealed that higher Rayleigh numbers values led to more pronounced fingering effects, particularly at higher impact angles. This suggests that both impact angle and Weber number must be considered together when analyzing bloodstain patterns.
Considering the characteristics of the Reynolds number discussed earlier, it can be observed that it influences and is influenced by the area ratio of bloodstains. To derive the correlation between the radius of a bloodstain and the impact of the blood droplets, the energy conservation equation for the spreading characteristics after droplet impact can be established as follows. The left-hand side of equation consists of Ke1 and Se1, which represents the initial kinetic energy and surface energy of the blood droplet respectively. These values are determined by the initial diameter and velocity of the droplet as follows. This equation expresses the initial kinetic energy of the blood droplet, and it derives by multiplying the kinetic energy per unit volume of the fluid by the volume of the droplet, which is calculated using the formula for a sphere. In the case of Se1, it represents the initial surface energy of the spherical blood droplet. It is formulated by considering the surface area of the droplet and incorporating surface tension. On the right-hand side of equation, Se2 and W corresponds to the surface energy after impact and the energy loss during the impact process respectively, and are determined as follows. By substituting the terms from the following equations into the equation as you can see here, the final equation can be expressed in the terms of the ratio between the diameter of the resulting blood stain and the initial diameter of the droplet as shown in this equation. Using this, we developed a predictive model for blood droplet behavior, incorporating blood stain pattern formation based on initial velocity, impact angle, and blood viscosity. The density, viscosity coefficient, and drag coefficient blood were set as arbitrary constants and parameters. Using the previously defined calculated ratio function, we computed the extent of blood stain spreading for various conditions. We also built to illustrate the relationship between initial velocity and the spreading ratio, with impact angle represented by color to observe whether a greater impact angle results in more extensive spreading. The result indicates that higher velocities and large impact angles generally led to wider blood stain spread, as confirmed through both computational modeling and visualization.
Blood stain analysis can provide critical insight into whether an incident results from an accidental fall or an external force. This study compared blood stains from the hypothetical case where a victim either slipped and hit his head on a staircase shelf or was forcefully pushed, leading to impact and subsequent rolling down the stairs. If the victim had slipped and hit his head on a staircase shelf, the resulting blood stain will primarily form due to gravitational force and impact direction. These stains will be circular or elliptical, and the impact angle theta could be calculated using the following formula, where W is the width and L is the length of the stain. When an external force is applied, blue droplets gain additional acceleration, causing them to travel at higher velocities. According to Newton's second law, F equals to ma, the velocity of the first blood droplets can be estimated using this formula, where d is the droplet diameter and c is a fluid dynamics constant. The calculated stain distribution indicated that the blood had projected upwards onto both the shelf and the staircase wall, forming small droplet stains. The impact angle ranged between 30 and 60 degrees, lower than typical fall-related stains, and the rapid dispersal speed suggested the influence of a strong external force. Furthermore, calculations of Reynolds and Weber numbers provided additional insights. Typical fall-related blood stains exhibit Reynolds number values below 10,000, yet the actual measured Reynolds numbers in this case exceeded 90 million. This extreme Reynolds number value suggested that the blood was not passively expelled due to a fall but rather forcefully propelled due to an external force. Based on the analysis of blood stain distribution and dispersal velocity, the evidence strongly suggests that the victim did not simply slip and hit his head on the shelf. Instead, the victim was deliberately pushed by another individual A, causing him to collide with a shelf before falling down the stairs. This study demonstrates how mathematical modeling can enhance traditional BPA, overcoming its limitations and providing a more precise forensic approach. By using mathematical calculations to model blood stain dispersion and velocity, we were able to establish that what initially appeared to be an accident was, in fact, the result of an intentional act. Our findings highlight the importance of integrating mathematical fluid dynamics with forensic science to improve the accuracy and relatability of crime scene investigation. This research underscores how advanced numerical methods can strengthen forensic conclusions and contribute to a more precise reconstruction of criminal events. Thank you for listening.